an inductance of 0.5 henries, a resistance of 5 ohms, and a capacitance of 8 microfarads are in series across a 220 volts AC power supply. Calculate the frequency at which the current flowing through the circuit becomes maximum. So ఇందులో ఫ్లో అయ్యేటువంటి ఫ్రీక్వెన్సీని క్యాలిక్యులేట్ చేయమంటున్నారు. దట్ ఫ్రీక్వెన్సీ ఈజ్ రెజొనెంట్ ఫ్రీక్వెన్సీ. Because series RLC circuit we are going to get a resonant frequency, and as well as find bandwidth and half power frequency and voltage across capacitance at resonance. ఆల్రెడీ ఇంతకుముందు మనం రెజొనెంట్ ఫ్రీక్వెన్సీని ఫైండ్ అవుట్ చేసాము, తర్వాత హాఫ్ పవర్ ఫ్రీక్వెన్సీని ఫైండ్ అవుట్ చేసాము, బ్యాండ్ విడ్త్ని ఫైండ్ అవుట్ చేసాము, క్వాలిటీ ఫ్యాక్టర్ని ఫైండ్ అవుట్ చేసాము. అదర్ దాన్ హియర్ one more calculation given, that one is voltage across capacitance. కెపాసిటర్కి అక్రాస్గా వోల్టేజ్ని క్యాలిక్యులేట్ చేయమన్నాడు. సో ఇంతకుముందు మనం క్యాలిక్యులేట్ చేసిన దానికి ఎక్సెసివ్గా ఇక్కడ వోల్టేజ్ అక్రాస్ కెపాసిటెన్స్ని క్యాలిక్యులేట్ చేయమన్నాడు. ఫస్ట్ మనం గివెన్ డేటా రాసుకుందాం. ఇండక్టెన్స్ గివెన్ L ఈక్వల్ టు 0.5 హెన్రీస్ అండ్ రెసిస్టెన్స్ గివెన్ R ఈక్వల్ టు 5 ohms and capacitance C equal to 8 microfarads, that is equal to 8 into 10 to the power of minus 6 farads, because micro in the sense that one is a 10 to the power of minus 6, and voltage given 220 volts. So here this one is a series RLC circuit. Okay, so this is a series RLC circuit. Then we are going to calculate here majorly to determine resonant frequency FR equal to how much, and bandwidth BW equal to how much, half power frequency F1 F2 equal to how much, and voltage across capacitance at resonance VC equal to how much. So these are the actually we need to find out, and here these are the given data values. Okay, then we will go to draw the series RLC circuit. So in this series RLC circuit, the given resistance value is 5 ohms and inductance value is 0.5 henries and capacitance is equal to 8 microfarads, and across these series RLC passive elements we have a voltage power supply is 220 volts. Then first we are going to calculate resonant frequency. So already we know that resonant frequency for both series and parallel circuit RLC circuit, FR equal to 1 by 2 pi root LC. So based on that formula we are going to calculate here resonant frequency FR equal to 1 by 2 pi root 0.5 into 10 into 8 into 10 to the power of minus 6, because capacitance is 8 microfarads. 8 microfarads in the sense 8 into 10 to the power of minus 6. So then directly we can take these values in calculator, technical calculator. Then we can get resonant frequency FR equal to 79.58 hertz. Then we are going to calculate bandwidth, second value. So the bandwidth formula for RLC series circuit, R by 2 pi L. So this is a standard formula for bandwidth. Okay, if any case we will go, I mean if any case we can get bandwidth for LC circuit in the sense, then that one is completely different. Okay, here for RLC circuit bandwidth is R by 2 pi L. So already we know that resistance value is 5 ohms and 2 pi L in the sense 0.5 henries. Then that is equal to, we can get 1.592 is the actual bandwidth of the given values. And then half power frequency, already we know that this one also we have solved in previous problem. So we have a two frequencies here, half power frequencies. One is a lower cutoff frequency, another one is upper cutoff frequency. First we are going to calculate lower cutoff frequency. Already here given frequency levels F0, F1, F2. So F1 is a lower cutoff frequency and F2 is a upper cutoff frequency. First we are going to calculate lower cutoff frequency. For a lower cutoff frequency we need to subtract R by 4 pi L from resonant frequency. F1 equal to FR minus R by 4 pi L. So here F1 equal to FR already we have calculated, that value is 79.58. We can substitute 79.58 minus resistance value is 5 ohms by 4 pi into inductance value is 0.5. So finally we can get 78.78 hertz. So that one is F1 equal to 78.78 hertz. That one is lower cutoff frequency. Then we'll go for higher cutoff frequency or otherwise upper cutoff frequency. Upper cutoff frequency F2 equal to previously F1 lower cutoff frequency, resonant frequency R by 4 pi L we can subtract from resonant frequency, but here upper cutoff frequency we can add R by 4 pi L for resonant frequency. Then we can get F2 equal to FR plus R by 4 pi L, in the sense 79.58. that one is the resonant frequency value, and our resistance value is 5 and 4 pi into inductance is 0.5. Finally we can get F2 equal to 80.37 hertz. That one is upper cutoff frequency. Then finally we will go for voltage across capacitance. So once you can see last problem already we have solved in that problem, resonant frequency and bandwidth and quality factor and as well as half power frequency. So other than those values, here extra value is voltage across capacitance. The voltage across capacitance at resonance is given by Vc equal to I into Xc. So Xc in the sense voltage across capacitor Vc equal to I into Xc. I into Xc. Here Xc is a capacitive reactance, I is a current value. Now already we know that capacitive reactance Xc is equal to 1 by 2 pi Fc. So based on that we can substitute Xc plus 1 by 2 pi FRC. FR in the sense that one is a resonant frequency, I in the sense that one is a flow of current. So across capacitor voltage Vc equal to, already we know that voltage V is equal to I into R according to Ohm's law. Based on that resistance replace with impedance Z value. Z in the sense here only we have a capacitive reactance. That's why here capacitive reactance Xc equal to 1 by 2 pi Fc. So F plus we can take a resonant frequency. That's it. So Xc equal to 1 by 2 pi Fc. Already we know this formula. Otherwise inductance in the sense XL equal to 2 pi FL. Xc in the sense 1 by 2 pi Fc. This is a standard formula for capacitive reactance. Capacitive inductive reactance equal to 2 pi FL. Okay, so here they are asking only across capacitor voltage only, no? That's why we are taking capacitive reactance Xc equal to 1 by 2 pi Fc. So here already we know that current I equal to V by R. R plus we can replace impedance value here. I equal to V by Z. So Z equal to R plus J into XL minus XC. Already we know this formula, impedance value for both inductance and capacitive case. So here this one is this circuit is RLC series circuit, no? So resistance plus XL inductive reactance minus capacitive reactance. Okay, so here inductive reactance is equal to capacitive reactance in the sense. Then what will happen? Impedance Z equal to resistance, because these two values are same in the sense we can get XL minus XC. This value is 0 here. Then that's why impedance Z equal to R. That's why only here I equal to V by Z. Why we need to take this Z is equal to R relation in the sense? This one is we need to calculate voltage across resonance on capacitive at resonance only. So resonance in the sense both inductive and capacitive reactance, net reactance is 0. Okay, now that one is a conditions for resonance. So that's why here net reactance XL equal to XC in the sense. Then this entire term will be going to 0. Then here Z is equal to R we got. So impedance equal to resistance and so I equal to, here I equal to V by Z, no? Z plus we can replace resistance R. Already we know that power supply V equal to 220 volts by resistance value is 5 ohms. Then we can get 44 amperes. So I we got 44 amperes. Already we know that 1 by 2 pi fr value also we know, and capacitance value also we know that. So those two values we are going to substitute here. Then we can get finally Vc equal to I into 1 by 2 pi frc. I we got here 44 by 1 by 2 pi fr. Resonant frequency value we got already 79.58. so that 79.58 we can substitute here, and capacitance is 8 into 10 to the power minus 6, it's mean 8 microfarads. Finally across capacitor voltage equal to 10,999.65 volts.